Okay, so this is part 2 of our chapter 2, exercise 4 in the Advanced GIS book. And so in this video, we've downloaded 4 different digital elevation models near the junction of Spanish Fork and Diamond Fork rivers just outside of Utah Valley. And so here they are shown with different kind of postage stamp sizes. So we've got 1 meter 2018 kind of psychedelic colors here as our smallest area postage stamp. So that's 2018 LiDAR. It's a 1 meter pixel size. And then this grayscale one is 2017 LiDAR. And I've just artificially colored these, right? But this is half-meter scale LiDAR collected along the Diamond Fork River, but with some overlap here. Then the smaller blue postage stamp is a download from Open Topography of the ALOS data set, 30 meter approximately, or 27.4 meter pixels. So this is our regional scale DEM. And then this thing is our 5 meter photogrammetrically produced digital elevation model from Utah in 2006. And so that's from a tile downloaded from the UGRC's raster data discovery app. And so to do topographic differencing, we want all of these grids to cover the same area so that we can compare them and their histograms reasonably and accurately. And also so that we don't have holes, no data, areas that we're comparing where it's apples and oranges, okay? So what I like to do then is to zoom in to where there is overlap, and we can go to a tool which is referred to as clip raster, or raster clip. And so that's under data management tools, raster processing, clip raster. In there, can actually draw a clipping polygon. And so if I turn off and on my underlying one, that's really kind of my smaller one. So maybe what I'll do is, and it doesn't have to be a square, although it is a little easier if it sort of is a square. But let's not worry about that. So let's turn this back on. So I'm gonna make my square following down like that to about here. I'll go over a little bit. The reason to go over a little bit is there's a landslide over here, so I'll make this polygon kind of follow the shape of this other one for a bit, and then that we've got as much as we want. So we'll go up this little drainage area here. It's kind of interesting, maybe for comparison. And then how far up here can we go? Go a ways, so keep this on. So maybe this will be our clipping mask. Okay, so we've created a clipping mask, and we can now use this polygon to clip all these from. And we can do it right in here right now, but actually we can save some time if we back out, right click and say batch process. And then we go next, and input rasters that we're going to do are the 1 meter 2018 data, the 2017 half-meter LiDAR, the 27 meter pixel ALOS, and the 5 meter data set as well. I'm going to not change the folder that these are in, which means it's going to go into my file geodatabase. It'll be a default Esri grid. It'll say clip, and then whatever the input was. input name. I probably should have changed some of these to be more obvious. But we want that output extent to be this clip raster output extent that we just made. And we need to check this box. Really critical that you check it. Use input features for clipping geometry. Okay. And then we can go to environments and make sure that all of them get output in NAD83 UTM zone 12 north. And then we can try and see if we can get the cells to align so that with different pixel sizes, that they are kind of on the edge. We can snap to whatever will snap to the smallest one. So the pixels kind of go to those edges. And the cell size, let's do the minimum of the inputs. Now, let's do the 2017 LiDAR. Okay, so basically what I've said, I think, is that I'm going to change the pixel sizes to be half meter so that we can compare them. Exactly. That means that we're going to kind of basically oversample the lower resolution ones. I think that's what's going to happen. We'll see. Okay, so we're clipping by that polygon. We're changing to make sure all output coordinate systems of the clipped rasters are going to be transformed into NAD83 UTM zone 12 north. And we are changing the cell size, I believe. Let's run that as a batch. This should take a minute. As we're doing that, I can talk about, when we're going to end up subtracting these different data sets, we kind of need some base map to kind of know where these differences that we might be seeing are in the landscape. So it's always a good idea to make a nice hillshade map of your kind of best resolution data set. And so I've already done that for the whole area for the 2017 LiDAR. You could make a slope shade as well if you want. Okay, so I'm going to turn off colorful inputs. And I could probably even remove them at this point, so I don't get confused. And so now my hillshade is on the bottom and these other ones are on the top. I'm going to turn them all off and add them back one at a time. And I'm going to turn off that clipping thing and move it to the bottom. Okay, so there's our hillshade. And I'm going to order these by resolution. The coarse is up at the top. 2018 is supposed to be 1 meter, and then 2017 is half meter. But remember that I changed these all. So 2017 should be half meter looking. So let's zoom in on some pixels. And let's see if we go to 2018, do we see any real difference? Doesn't look. Okay, so as we go to the 5 meter one, you can kind of sense a gradient that looks like bigger pixels. And again, here, so it might not have changed the pixel sizes. How do we tell? We right click, go to properties, look at source, raster information. Yeah, it did not change the pixel sizes. Okay, so this indeed is a 5 meter data set, and I can I can add that here at the end just to be clear. That already says 27 meter. I believe that's true. Yeah, about. And then this one must be 1 meter. So let's check to make sure. Yeah, about 1 meter, pretty much. Okay. Okay, so great. Let's check if this one got converted to NAD 83. Spatial reference, UTM, NAD 83, zone 12N. Okay, good. So they're all in the same horizontal coordinate systems. That's good news. Now we know that only the LiDAR data sets are in the same vertical datum / coordinate system. The other ones are older geoids. So we have to be cautious about our interpretations of differencing those because of that. Okay, so we have almost registered them so that they can be differenced. Let's see about the edges. So as we get to the edge of here, especially where it's kind of at an angle, do we have any issues with that? Yeah, we do. Do you see that on the edge here, we've got some edges that overlap or underlap with each other. And so that's going to be a little bit weird. So doesn't mean that we need to like necessarily do anything. We can probably go ahead and just difference them right off the bat. But it does make you think you might want to uh, kind of cinch things down a bit, if that makes sense. So what we could do potentially. Okay, so let's see. So we could do a couple of different things. So with those kind of coarser data sets, yeah, and also, yeah, I'm curious, like this ALOS uh, one that we converted the horizontal coordinate system looks a little weird. Let's run a hillshade on that to make sure it's not too weird. So let's input that ALOS and we'll call it hillshade ALOS. Um, Run it. It's not going to look good because it's 27 meter pixels, but it shouldn't look too wild. Where is it? It does seem to have a little bit of some sort of pixelated distortion, like maybe the horizontal coordinate system wasn't transformed in the best way by doing it in process like we did. So it might have been a better idea to first change the coordinate system and then do the clip. So keep that in mind. That being said, the hillshade model looks okay for what it is with these 27 meter pixels. It's not great. I'm gonna remove that. We could go back, right? We could go back and do that if we wanted to, but I'm gonna avoid it for now, just for the sake of time. Okay, so as I said, is probably gonna merge part 2 and part 3. And so in part 3, we're going to do the differencing of those DEMs and see what we see. And so to do differencing is kind of pixel by pixel change. Um, Interesting. Raster compare. That's not what I was looking for, but let me just see about something. Raster data set. Um, so um, we can resample the raster data set so that they potentially are kind of on as we're subtracting half meter from a half meter pixel, we're not crossing over to a neighboring pixel. It's not really going to improve the result, but it might make it look a little less artifact-y, if that makes sense. So if we output that as half meter and we go to like a cubic convolution resampling, make it a little smoother, and we snap it to the 2017 data, and we make the processing extent the 27 meter data, and run it. Let's see how that goes. So if I put in front of it now the 2017 LiDAR and change the coloring on that, turn it on, you can still see that we have issues, right, with this sawtooth pattern sitting on the edge there. Okay, so and then if we switch up the order, we can also see areas where they stick out. And so this would be another potential reason to do this, right? So we can transform them into the same size pixels that are kind of exactly on the same points, or their grid cells kind of cross each other. We can then use a clipping mask and get the same exact output. So let's just check to make sure. Yeah, now the new one is a really oversampled half meter ALOS data set. So we could do that with the other ones as well. If we go back and input this one, the output would then become clip clip 5 meter resample, we'll call it. And then I'll do that for the LiDAR as well. So first as I'm doing that, I'm doing a snap raster, which should kind of snap those pixels to the same kind of edges of the pixels, which is important for the differencing as well. Okay, so now we go to the 1 meter and we clip 1 meter resample. I'll put 2018 on that just to be clear. You may have noticed that the ALOS resample doesn't have decimals. The ALOS data doesn't have any decimals on those values, whereas the other data sets do have decimals. Okay, so now they've all been resampled, and if I bring back my clipper, we can see that, if we go to the 2017 clipped one, pretty much right on there, but if we get really zoomed in, we see it's not quite, right? And so because the raster is pixels, right, it has to have that jagged saw. So I think now basically if we want all these to be exactly on the same positions, we actually need to go ahead and make a different clipping mask. So go back and we go to clip raster again. And this time I'm going to make that polygon just a little bit inside of where it was before. They all have the same jagged edge. Okay, good. So that's made. So I'm going to back up. I'm going to batch it again. And like batch on top of batch. It's going to say clip clip. That's okay. But that's the way it's going to go. So when we enter the different ones, including the 2017 clip. So all of them, all the resamples plus that. And now we're going to say, maybe we do it this way. We percent name, which will be whatever was the input. And then afterwards, we could do underscore reclip. Okay. And we shouldn't have to do too much here, but let's just make sure they're all snapped. That one. Oh, better stop that. Forgot what I was doing. You got to go back here and choose that and use input features. Okay, so this kind of registers potentially all the pixels to the same half-meter space in the real world. And then in addition, we've already kind of got them in the same horizontal coordinate system. Again, the vertical datum, it's not quite what we want it to be for some of them, but it's okay. I'm going to remove the other ones. Okay, and I'm going to turn off the clipping feature now. If I zoom in, I think all the sawtooth pattern should not change. Oops. Back in some more, turn them on now. So we got the same kind of jump right here. Turn on the next one. Off. Looks good. Okay, yeah, it looks good. Okay. So now they all exist over the same space. Now we will do our vertical differencing. And again, the most reliable one's going to be the LiDAR differencing because it's in the same vertical datum. If you do need to do this in a professional way, you're going to need to convert those other vertical datums, the values underlying the pixels need to be referenced above the same kind of vertical positions. So think about it as like the same sea level. Well, one sea level is different than another with time. But in this case, it's about gravity. So the equal potential surface, roughly representing gravity, as we know it at this position, has changed with time because we have better and better models with it. So it shouldn't be hugely off, but it could amount to some centimeters of vertical change that are kind of uniform across this area that might be part of the signal. How weird is that going to be? Not necessarily that weird, given that the vertical errors on these things are already on the order of centimeters. So, okay, let's see what we can do. So to do vertical differencing, we go to Spatial Analyst, we go to Map Algebra and Raster Calculator. And the differencing, the most logical way to do this is always the newest data set minus the other data set you're comparing it with. So I'm going to compare it to 2018 minus 2017. And so I'll say that. So I'll call it diff 18 underscore 17. And that will be a difference between those two. Okay, so one thing that's come out of that difference map is some very high white values that we see in here. And those are likely due to, since they're positive, um, where the 2017 data had maybe no data, essentially it's like 2018 values, so above the geoid, 1563 meters, minus 0. And so those aren't very real. So if you don't like that, which I don't, the next thing I would do is do a conditional operation. So I'd erase this, and then I would say conditional that diff value, wherever it's less than, say, 1,000 meters, is probably real. So then afterwards we'll return it, but otherwise we won't return it. Okay, so there'll be holes there. And we'll call this diff 1817 cut. So you see the negative values, -8, all the way to 1563. That's what we're getting. We're kind of making it more realistic for those, getting rid of those holes. The holes may be bridges or some weird pixels. There's no returns. There's quite a few of them across the landscape. So we want to be careful of those. Those aren't our real data. And all these processes are taking some time because this half-meter grid making fairly big file sizes. We can also see on this difference map that it's almost like we can see the topography through the difference. And so that just tells us that the differences are tied to topography in some way. They have a bit of a hillshade effect. That could mean that one of the LiDAR's data sets is not looking through the LiDAR as well as through the trees as well as it should be. Or it could be that erosion and non-erosion are really kind of tied to like where there is and isn't vegetation on different sides of the hill slopes. Could also be tied to like slight vertical issues as well, where maybe there's an offset horizontally that's kind of giving a kind of effect that's making it look a bit of a hillshade. So something to be aware of. But a lot of times when you do vertical differencing, you will get what ends up looking like a hillshade in the background in a grayscale. And that can tell you that there's some misalignments. But we'll change that signal a bit here in a minute. So that didn't, get rid of all those holes. I can still see some 800-meter values for whatever reason. Interesting. I'm not going to worry about that too much right now, but we could kind of refine that. We could do conditional wherever it's less than 100 and then give it back. Because we wouldn't expect 100 meters of change to be anything greater than that to be real. There's no skyscrapers here. Okay, so yeah, you could go and run that again. Now we can go back to the 2018 and then go up and subtract. The next youngest thing is actually the ALOS data from 2011. And this would be diff 18_11. It's not a cut because I haven't done anything yet with that. So here, it's kind of wild to look at. You can see a lot of artifacts coming in from the pixelation of the original large pixel sizes. We can also see some channels and things showing up, which probably has to do with differencing the smooth topography of the large pixels versus the kind of detailed topography which shows channels. So that's interesting what happens when you do that. Okay, so let's run the other one. So we'll get rid of, we'll go to the 2006, the 5-meter. Say that 0.6. Notice when we ran that last one, we didn't get wild values. It's only when we have maybe like not the best LiDAR or we have some holes, things like that, that we get those wild numbers. Okay, so this is an interesting result. Seems like in here we are seeing in the difference map maybe the edges of channels and a lot of things in the floodplains. Not so much in some other places. Okay, so I'm going to turn off those. So we have now 3 difference maps. I've just done 18 minus each of the others. So we have over a 12-year period, over a 7-year period, and over a 1-year period of change. Now, to look at these better, it's probably better not to look at them black and white. So what we usually like to do for looking visually over difference maps is to make them kind of one color scheme to another, where one side is positive and one side's negative. And I don't know if you like it like that. Positive is blue and negative is kind of brown red. Could go like this. Neutral is yellow. Whatever works for your eye is reasonable, but you kind of gonna go to neutral in the middle and different colors to either side. And so, yeah, I kind of do like this one, but I might invert it where positive is red and negative is cool. Okay, that's great. So this is over the longest time period. And we can do some more adjustments in here, right? We can change from percent clip to standard deviation. This is over the whole range of values of the data set. You can also change it to a custom range of values where you just want to see like what's negative. You can saturate at -1 and 1. Then it kind of just shows you where things are either positive or negative or neutral. And so like in terms of big changes, there seems to be some blobs in these areas down here. So those blobs are kind of down here in this gully area. There's probably trees in there. And remember over here, different blobs on one side versus the other. Positive, so it's gone up or it's gone down. Interesting. So uniformly, it seems to have mostly gone down, which makes sense because LiDAR should see under the trees, and the earlier one had trees. But then to have big blobs means some sort of deposition or something. And so we have potentially some of that going on up here, right, where this new home site has been developed. Phil has been brought in to put that home site there. Seems like we got something similar going on along this road. And so we do see some human-induced change there in this image. And then down in the channels, change is a little less clear, but there may be some. If you really want to look at a certain area like this, you could go to dynamic range, where it's just looking over this area. And then the thing about that is just showing you negative to positive, and you kind of lose that effect of whatever you set it to the exact custom amount. So you got to be careful with that. We go over here where there was this landsliding. If I turn this off, this is what's called the Schertz landslide. You look at change over there, it generally shows as higher values. Interesting. And higher on the edges of the landslide, maybe a little bit more than the middle. Which could relate to like movement and forming kind of like levees and things like that. But it's not 100% clear to me that's exactly what's happened, but it could be that we're seeing landslides moved. Okay, so that's over a long time period. let's turn that one off for a minute and let's do the same thing, but first let's go back to the data set. That's over the whole data set. 2 standard deviations. We're going to look in the next video at kind of getting into some of the details, like if we wanted to quantify exactly what's going on there, does that actually show the landslides moved or not? But let's first just get all of them kind of looking the same for a minute. So I'll turn this one off, go to this one, change it to the same color scheme. I believe I inverted it. Turn it on. Standard deviation. Now you can't see as much through these huge pixel artifacts, as it's smoothed across the topography there in the difference. And so maybe we never see much out of that data set. So I'm going to turn that one off, go to this one. This is 1 year of change, same color scheme, invert it, standard deviations 2, turn it on, let's see what we got. Hello. Might need to build pyramids or statistics for this particular data set. It seems to be slow. If you run into that sort of issue, what you can do is go to the catalog pane in this geodatabase. This thing is called diff 1817 cut. Right click on it and you can calculate statistics, run that. That might speed it up. And then also build pyramids. That will also speed it up. You can see it's trying to load here, not very successfully. Okay, so I guess we'll end this video here, part 2 and part 3, registering the data sets so that they occupy the same pixel areas or in the same horizontal coordinate system, and then differencing them in raster calculator. In the next video, we'll get into comparing the difference maps more visually with their histograms and using profiles.